In majority of chemical industries today, a reactor is an important equipment in which raw materials undergo chemical changes to form desired products. A chemical reactor is also known as a device for controlling and containing chemical reactions. Before running a chemical process, it is very important for us to choose the ideal type of reactor. A reactor is chosen based on the mode of operation. Generally, there are two types of commonly used reactor for chemical processes in chemical industries, which are the batch and continuous reactor. Both of it has its fair share of advantages and disadvantages. For experiment, we are using batch reactor to undergo saponification process. Batch reactor is a reactor where the reactants are added together at the beginning of the process and products are removed at the end of the reaction. Saponification is generally a process for making soaps. For the experiment we conducted, we are using ethyl acetate and sodium hydroxide to react and produce soap. Basically, the two main objectives of the experiment is to prepare the calibration curve for conversion against conductivity and also to study the batch saponification reaction of ethyl acetate and sodium hydroxide.
To achieve the objective of this experiment, which is the experiment to batch liquid reactor, we need a proper methodology or procedure. So in this experiment, the methodology is divided into two parts. Which is the first part is to prepare the calibration curve. The second part is to study the saponification reaction between the sodium hydroxide and ethyl acetate. Okay, here are the 5 solutions that we need to prepare, and each solution is different in the term of the molarity and the conversion. The reaction curve is a graph of conversion versus conductivity. We are able to plot this graph when we get the value of the conductivity from the software in the computer. Okay, so my partner Baldip will explain the detail about the solution, the molarity of the solution, and the conversion of it.
The material used in this experiment, we use 0.025, 0.05, 0.075 and 0.1 molar of sodium hydroxide. We also use 0.025, 0.05 and 0.075 of sodium acetate. Third, we use 0.1 molar of ethyl acetate, and also lastly the ionized water. The apparatus used for this experiment is a batch liquid reactor. This reactor is made up of a top and bottom stainless steel plate. The reactor is vacuum insulated by an outer glass plate. The reactor consists of a stirrer system, a conductivity sensor, a temperature system, and a cooling coil and also a heater. For this experiment, the temperature is constant at the room temperature, thus the cooling oil and the heating coil is not used. Next is the control panel. This control panel is necessary for the modules for the data that we require for the experiment. It consists of all important necessary electrical components for the controlling of the operation of the unit. It displays the conductivity values detected by the sensor in the reactor. Next, we use the data acquisition system. This data system consists of a personal computer, ADC modules and instrumentation for measuring the process parameters like conductivity and conversion. Feed inlet system. Two 20-liter feed tanks equipped with pumps and flow rate system. Each reactant was pumped into the feed tank and then into the top of the batch reactor. Product waste tank. A 50-liter stainless steel tank is used to collect the drainage before being discharged.
Okay, so how to do this experiment? How to plot the calibration curve? So first, after we prepare the solution, we put the solution into this reactor, to the batch reactor, through this hole. Then, we fix the stirrer speed, on the stirrer speed, and we fix the stirrer speed. For example, 50 RPM. But make sure the stirrer speed is constant for the other snack solution, because we want to get the calibration curve. So, after about 5 minutes, we are getting the conductivity values for one solution. Then repeat the step for the other solution. Then we get the 5 conductivity value, and from there we can plot the conductivity conversion versus conductivity graph.
Great.
the amount of the unreacted sodium hydroxide then is determined by the direct titration with the 0.25 molarity of the hydrochloric acid. Then the final step is the real concentration of the ethyl acetate was recorded. So in the last experiment, the experiment part 2, we are using the 1 liter of 0.1 sodium hydroxide and 1 liter of 0.1 ethyl acetate to undergo the saponification process. Before we added these two solutions into the batch reactor, we must first make sure that the valve 11 is closed. Then we must switch on the pump 2. After that, we must add the 1 liter of 0.1 molarity of the sodium hydroxide to the reactor. After the solution was added into the batch reactor, we must close the pump 2. Then we open the pump 1 and add the 1 liter of 0.1 ethyl acetate into the batch reactor. After the 1 liter of 0.1 molarity of the ethyl acetate was finished added in the batch reactor, we must close the pump 1. Then we must switch on the stirrer. Then we must switch the stirrer to 50 RPM. Then using the computer software, we start the experiment. This software will get us a conductivity value from our reaction, and from there we must take the conductivity and record it in the appropriate table. After we get the constant conductivity value, we stop the experiment. Then we must clean the reactor. So how to clean the reactor? So to drain the reactor, we must first open the valve 11 to let the solution in the reactor drain out. Then we close it again and put 1 liter of distilled water into the reactor. Then let it mix about around 1 minute or 2 minutes. Then open it again, the valve 11. Then the reactor is clean and close it again. Repeat the step that I said just now for the different stir speed, which is 100 RPM, 150 RPM and 250 RPM.
Experiment A. Preparation of the calibration curve for conversion versus conductivity. The solution was prepared according to the value below and the conductivity value was recorded. From the calibration curve, we can see that the conductivity increases. Conversion for sodium hydroxide decreases with a negative gradient with a constant stirrer speed of 316 RPM and room temperature of 27 degrees Celsius. From the graph plotted, we are able to obtain the following information. Y equals to 0.0956x plus 1.9138. Based on the graph, the y-axis is the conversion of sodium hydroxide and the x-axis is the conductivity values. From the R-square value obtained, negative 0.9984, which approximates unity, we know that the regression line fits well with the data, which validates the correlation between conversion and conductivity. The slope m, negative 0.0956, and intercept c, 1.9138, was used for experiment B and it was keyed into the computer software. The conductivity is a measure of amount of ions in the batch reactor. In the context of saponification process, the reaction between ethyl acetate and sodium hydroxide will produce sodium acetate and ethanol. High conductivity illustrates that there is high molar concentration of sodium hydroxide ions, while low conductivity illustrates that there is a high molar concentration of sodium acetate than sodium hydroxide ions. Therefore, the high production of sodium acetate, which stimulates high conversion, will show a decrease in conductivity values. Experiment B. Batch saponification reaction of ethyl acetate and sodium hydroxide. Discussion on the order of reaction of each stirrer speed. Once we have determined the calibration curve from the first part of the experiment, we can use it in order to carry out the second part of this experiment. In this part, our aim was to study the batch saponification reaction of sodium hydroxide and ethyl acetate. This includes determining the order of reaction as well as the effect of changing the speed of the stirrer on the reaction. The manipulated variable in this experiment is the speed of stirrer. The constant variables are first, molarity of sodium hydroxide solution, second, molarity of ethyl acetate solution. We have to determine the order of the reaction to study the batch saponification reaction of ethyl acetate and sodium hydroxide. The stirrer is set to 200 rpm. In order to determine the best fitted line, we plotted 3 graphs: first order, second order, and zero order. The graph with the best fitted linear line will indicate the order of the reaction. For 200 rpm, it can be observed that the second order graph gives the best linear line compared to the first and zero order with the R-square value of 0.77. Thus, it can be concluded that the reaction favors a second order reaction. For 150 rpm, it can be observed that the second order graph gives the best linear line compared to the first and zero order graph, with an R-square value of 0.7743. Therefore, this reaction favors a second order reaction. For 100 rpm, it can be observed that the second order graph gives the best linear line compared to the first and zero order graph, with a R-square value of 0.8555. Therefore, this reaction favors a second order reaction. For 50 rpm, it can be observed that the first order graph gives the best linear line compared to the zero and second order graph, with an R-square value of 0.9491. Therefore, this reaction favors a first order reaction.
Today we'll be talking about the errors and modifications in the batch liquid reactor. The first error is that the batch reactor was not fully drained when changing of the solution. This causes a residue to form inside the reactor. A modification to be done is to always ensure the reactor is completely drained from previous solution before adding in the new solution. This is to avoid inaccuracies in results. The second error is that the rate of filling of batch reactor with the solution at the beginning of the experiment was too slow. When the filling of solution is too slow, the reaction might have already started before we had the chance to start the timer. This causes inaccuracies in the results. The reason we did not use a pump for this is because the pump was functioning poorly. So the modification we need to do is to use properly maintained pumps to pump the solution from the feed tank into the batch reactors.
To conclude, we have achieved all the objectives of this experiment. In the first experiment, we are able to prepare the calibration curve for conversion and conductivity, and able to obtain the linear equation, which is y equals to negative 0.0956x plus 1.9138. This equation is then used in the second experiment. From the graph, we can see that as conductivity increases, conversion for sodium hydroxide decreases with a negative gradient. The second experiment, sodium hydroxide and ethyl acetate are reacted in a batch reactor. We managed to get the order of reaction for each different stirrer speed, which is 50 rotation per minute, 100 rotation per minute, 150 rotation per minute, and 200 rotation per minute. Basically, the best straight line of order of reaction and time shows the correct order of the reactions.